You can buy the fastest CPU, massive hard drives, and gigabytes of RAM. But sitting on a desk, all of that expensive silicon is completely useless. It is just an inert pile of metal and plastic. If you simply plugged it in and let the hardware run, the result would be instant chaos. Millions of electrical signals would flood the circuits, fighting to use the exact same pathways at the exact same time, immediately freezing the entire system in a bottleneck. To turn that dead electricity into a functioning machine, you need an arbiter. An invisible layer of software acts as a command center, translating human intent, like clicking a mouse or tapping a screen, into organized hardware action. We call this the operating system. But how exactly does this software prevent dozens of complex, demanding programs from fighting over a strictly limited pool of physical resources and crashing the machine? The operating system acts as the ultimate defense against digital chaos. It brings those dead electronics to life by ruthlessly managing three core hardware domains: the processor, the memory, and the storage. The moment you hit the power button, a strict sequence of events begins. A tiny chip on the motherboard runs basic firmware called the BIOS to wake up the physical components. The BIOS then locates a small program called the bootloader, which pulls the operating system off your hard drive and loads it directly into active memory. Once awake, the OS presents you with its outer layer, known as the shell. This is the user-facing interface, whether it's a command line or a graphical desktop like the original Macintosh shown here displaying hello. It exists entirely to provide human convenience. Beneath that friendly exterior lies the kernel. This is the highly protected, invisible core of the OS. It bypasses the user entirely, communicating directly with the physical hardware to ensure every task gets the exact electrical throughput it needs. While you are casually interacting with the shell to open a folder or play a song, the true war for resources and stability is being fought by the kernel underneath. That war starts with the first domain, the CPU. To the operating system, there is a strict difference between a program and a process. A program is just passive code sitting quietly on your hard drive. But the moment you double-click it, the OS loads it into active memory, and it becomes a process, a live entity requiring immediate CPU attention. To keep the CPU from ever sitting idle, the OS uses multi-threading. It takes a single heavy process, like rendering a video, and slices it into smaller concurrent tasks called threads. These threads run side by side, squeezing maximum efficiency out of the processor's cores. Modern operating systems push this further by using process isolation. Take Google Chrome, for example. Instead of running the entire browser as one fragile process, the OS places every single tab into its own secure, isolated box, a technique called sandboxing. If a heavy web application in one tab crashes, that specific process dies, but the rest of the browser remains completely untouched. By forcing strict boundaries between processes, the OS guarantees that a single failed task cannot take down the entire system. The OS then tackles the second domain, memory or RAM. Here, it faces a massive physical constraint. Modern software, like high-end video games or complex 3D modeling tools, routinely requires vastly more active memory than the computer actually possesses. This diagram illustrates how the OS creates an illusion called virtual memory to solve the problem. Using a technique called demand paging, the OS calculates that a process usually only needs about 10% of its code at any given exact second. It locates the specific fragments of code required right now and moves those active blocks into the much smaller physical RAM. As you continue working, new code needs to be loaded. To make room, the OS employs algorithms like least recently used, or LRU. It constantly monitors which blocks of memory haven't been touched in a while, and quietly swaps those older pages back out to the hard drive, freeing up space for the new ones. If you open too many heavy applications at once, this elegant swapping mechanism breaks down. The OS enters a catastrophic failure state known as thrashing. The system becomes so overwhelmed that it spends more time frantically swapping pages in and out of the hard drive than it does actually computing your data. When it works properly, effective memory management is a brilliant sleight of hand. It tricks massive resource-heavy software into functioning flawlessly inside incredibly tight physical hardware limits. The third and final poor domain is long-term storage. To the physical drive, your data is just a raw, unreadable ocean of bytes. It only becomes useful because the OS imposes a strict organizational structure over it, called a file system, which categorizes the data into directories, assigns unique names to files, and enforces strict access permissions. But organizing the data is only half the battle. On traditional hard drives, the physical challenge is retrieving scattered pieces of information across a rapidly spinning disk using a tiny, mechanical read and write arm. If the arm simply chased requests in the exact order they arrived, it would violently jerk back and forth, wasting precious time. As this diagram shows, the OS organizes the requests using the scan algorithm. Just like an elevator picking up passengers on its way up a building, the OS forces the mechanical arm to sweep smoothly from the inner edge to the outer edge of the disk, picking up data sequentially along its natural physical path. Engineers later refined this into C-scan, or circular scan. In this optimized variant, the arm sweeps in only one direction, reads the data, and then snaps rapidly back to the starting point. This prevents data at the extreme edges of the disk from waiting too long, providing mathematically uniform response times across the entire drive. By calculating and optimizing these mechanical movements, the OS prevents erratic wear and tear, effectively transforming slow, fragile hardware into a highly reliable data vault. While you move your mouse to open a single file, the operating system is quietly executing millions of these microscopic decisions. It balances CPU threads, swaps memory pages, and calculates physical disk trajectories every single second, completely invisibly. This foundational architecture scaled seamlessly into mobile computing. As seen here with the finger interacting with an early iPhone, the OS evolved to instantly manage complex new hardware inputs, translating swipes on a touchscreen, shifts in an accelerometer, and signals from a GPS chip into smooth, real-time software responses. That same scaling principle enabled modern cloud computing. Virtualization tricks a single server into acting like hundreds of computers, running independent operating systems inside one tower. This evolved into containers, which strip away the bulk. They allow applications to share one base OS kernel while keeping top-level data strictly isolated. Whether it is running a smartwatch or a sprawling cloud data center, the ultimate triumph of an operating system is its absolute invisibility. It flawlessly orchestrates millions of electrical signals, physical movements, and software demands, precisely so you never have to think about it.